I see.
I think that's a perfect segue for me to start the Quantum Seminar. So welcome to the Quantum Seminar, everybody. We are super happy to have Ignacio Cirac here, and we already went a bit over his CV with Ramir. Currently, he's leading, I mean, I'm sure everybody knows him, but I'm just summarizing it a bit. He's, for the last nearly 20 years, a director of the theory division in the Max-Planck-Institut for quantum optics in Garching. And like every physicist with influence, he has a Wikipedia page where you can go in great detail over all his career steps, like that he did a PhD in the University of Madrid in '91 on interaction of two-level atoms with non-classical states of light. Went to GIDA, we already discussed that with Peter Zoller, then came back to Innsbruck, where he had a brief 5 years professorship in the theoretical department. And since 2001, he is director in quantum optics, and he has amassed enormous amount of citations in his work. And I just went over his Google Scholar account. He has an H index of 144 with 100,000 citations, which I don't know, find impressive. And if you sort by most cited papers, it's like the just submitted Quantum Manifest to the German Bundesregierung, addressing all the pillars of quantum technology. The first one is quantum computing with cold trapped ions. The second is cold bosonic atoms in optical lattices, so quantum simulation, and then long distance quantum communication as a third most cited paper. So I find that pretty impressive. He also gets prizes every 3 years, roughly. So the last one was the Max-Planck medal, the most influential or the most important German prize of the German Physical Society, together with a new prize from the Chinese government, I believe. Also, if you look at it, who received it, it's I had it here somewhere. It's the Mikius Prize or something. It's a new prize, was established in 2018 for achievements in quantum science, and he received it with Peter Shaw and David Deutsch and Peter Zoller, so a lot of important people. But maybe the best endorsement came 2 days ago or 1 day ago by a PhD student in our group, and he said, his lectures are awesome, and they partially motivated me to do my bachelor thesis in quantum computing. When I saw he's doing the quantum seminar, he had to free basically his working slot in our group. We have working slots. He had to free it for today because he knew he couldn't miss it. So we are very happy to have you here, Ignacio. Please give us your talk.
Okay, well, thank you very much for this very kind introduction, Arne. It's a great pleasure to be here and to share with you some of the work that we have been doing and some other people have been doing in the context of quantum simulation. So that's not going to be a very deep talk, very much detail, but I want to give you an overview from some perspective on the field of quantum simulation, and it will be more the theoretical perspective. So what we expect that it will be possible to do with, let's say, next term quantum computers or analog quantum computers. And only at the end, I will go into some physical systems and just mention some applications in some physical systems. Okay, so you're very well aware of the big hype that we are living at the moment on quantum computing. It appears in the media. I don't know if if I open Google in my cell phone, then it always gives you some last news. I get every day that, there is a new breakthrough in quantum computing, something like that. So we're really living a very special time in quantum computing. And in fact, so most of the the information that has come to the media is based on the fact that we know that if we had a quantum computing, like a quantum computer, a scalable quantum computer, that we could solve many problems. And in fact, there are quite a few, I mean, more than what people typically imagine that could be solved, it could be accelerated by a quantum computer. However, we don't have scalable quantum computers, and it will take a long time to build these scalable quantum computers because it's a very difficult task. I mean, just making a back of the envelope estimation of how many qubits do you need in order, let's say, to factorize numbers with a fault-tolerant quantum computer get completely outreaches. However, what we have are then like the first generations, the first prototypes of quantum computers, which are noisy. Maybe they work in an analog way, not in a digital way. They have errors and they have the order of 50, 100, 200 qubits. And there is a lot of interest now on what can we do with those systems. So Google published a paper 2 years ago showing that indeed, with the system that they have, one of these so-called noise intermediate scale NISQ device, they could perform some quantum computation that goes beyond anything that we can even imagine to do with a classical computer. And so that's why, I mean, many people, including me, believe that these devices could perform some things that we cannot do with classical computers. However, we don't know what yet. So I think that there is very little evidence of what can be solved with this kind of first generations of quantum computers that we have at hand. I mean, one exception in which we know that indeed this can help us is in quantum simulation, in solving quantum many-body problems. And so these quantum many-body problems appear typically in science. So when you want to solve, for example, problems in high energy physics, you want to solve the equations corresponding to QCD or QED or standard models or whatever. These are many-body problems, or the ones that appear in material science when you have many electrons, or the ones that appear in chemistry when you have also many electrons now attached to some nuclei. And all those share this peculiarity that they're very hard to solve, or they are very hard to describe with classical computers. And the reason is very simple, and I'm sure that all of you know that, is that in any of these problems, so typically we want to put it in a classical computer, then what we will do is that we will discretize space. So for example, in the case of a solid, then the discretization is typically given just by the solid itself because the ions are at some periodic positions. But in high energy physics, what you do is you discretize the space and then you put it on a lattice. In chemistry, I mean, you discretize orbitals, but at the end you have something like a lattice. At the end, you can describe any of these problems like a set of quantum systems just arranged in some geometry that are interacting with each other according to some Hamiltonian. And even if you have the simplest system, like two-level systems, so like qubits, then you want to predict any physical property corresponding to the system, then you will have to solve a many-body problem. You will have to find either the ground state or the dynamics generated by this Hamiltonian. And if you even want to write down what is the state, then it will be a linear combination of all possible configurations. And since you have, since there are 2 to the power n configurations, you have n qubits, then this means that the state will be described in terms of 2 to the power n coefficients, complex coefficients, and all the physical properties are encoded in those coefficients. So in practice, if you want to compute physical properties, then you will have to compute these coefficients, and then you right away come to the problem that you will need a memory that grows exponentially with the number of qubits that you have, because you have to store 2 to the n coefficient. And also at the same time, since you will have to do at least one operation per coefficient, then you have to do 2 to the n operations, and then the time that it will require to do any calculation would also have an exponential growth with n. And that's very peculiar, and sometimes this is not so much emphasized. There are problems like the factoring problem that you can solve with a quantum computer, and in which you can have an exponential gain in terms of time. However, in quantum many-body problems, then you have an exponential gain if you use a quantum computer, both in memory and in time. And in fact, you can, I mean, people in computer science have asked, so what happens if I only want to use a fixed amount of memory, or let's say a memory that only grows polynomially with the number of qubits. Like I would like to, if I have n qubits, I would like to use n bits. So then it's possible to solve these problems related to many-body physics, but then there is an overhead in time. And in fact, this overhead in time makes it super exponential in time. So that's why, I mean, this exponential dependence, both in memory and time, is why these many-body problems are very special for quantum computers and will be very special. I mean, can compete very well with classical computers because they are extremely difficult in classical computers. And so that's what is behind the idea of my talk. So, okay, so there is a set of problems which are very, very difficult, more difficult than any other problem, let's say, in a classical computer. So why don't we use a quantum computer, even these first generations of quantum computers? Because even if there are some errors, then still this huge advantage then may still show up and allow us to solve some of these problems. In fact, that's something that was realized many years ago. So people quote this paper by Richard Feynman, in which he realized at the time, there was a time of QCD. It was just discovered a few years ago. And so people had the equations of QCD, so they had to solve them, and they had computers. They had lattice gauge theories appeared at that time. And then they say, well, it's a problem of solving them with computers. So we know already, we can solve QCD. But I mean, people very soon realized that this was not possible, that solving these equations, because this was like a quantum many-body problem, was very difficult. And that's how Einstein, in a conference that had nothing to do with QCD, was on the problem of computation. So he came up with this paper saying that these problems are very difficult to solve with classical computers, but if we had a quantum computer, it would not be so difficult. And the idea is that if you have a quantum computer or you have a quantum system, then you don't have to store all these coefficients, these 2 to the n coefficients that I mentioned before. You just have to prepare your state of n qubits on that state. So you need n qubits in order to represent n qubits, not 2 to the n bits in order to represent n qubits. So the idea is to use now quantum systems to store the states of your system. And this automatically has a gain in memory. So the memory then in a quantum system, in a quantum computer, only grows linearly with the number of qubits that you have, obviously, trivially. And what he argued, and some people later on argued, that even time can also grow not exponentially for certain kind of problems. And so that's a little bit what I want to do. First, I want to just go through the different problems that appear in many-body systems and see, so what are the algorithms that exist? What is the time that it requires? And whether with these kind of first generations of analog quantum computers, NICs devices, then there is a hope that we will solve some of these problems better than with classical computers. Okay, so that's the setup that I'm going to consider for the rest of the talk. I'll have a set of qubits, but could be fermions, could be any other particles on a lattice arranged to some geometry, whatever geometry. I'm giving a Hamiltonian, and this Hamiltonian just describes the interactions between these spins or qubits or whatever they are. And I'm going to assume that this Hamiltonian is what is called local. So this means that this is a sum of terms that involves just few particles that are at some location. So for example, it could act on these 4 green particles, another one could act maybe on these 6 particles. And so these are what we call either finite range interaction Hamiltonians, or I mean, we call them also local Hamiltonians. And then I want to revise some algorithms that exist to describe the dynamics. Namely, if I start with some initial state that is not an eigenstate and then let it evolve, how the physical properties will change. And if I want to compute the physical properties, how can I do it with a quantum algorithm? And if there will be a gain with respect to a classical algorithm. Also the 0 temperature. So if I cool down the system up to the ground state, then you want to compute physical properties in the ground state. So how difficult is that? And then I'll talk also about finite temperature. And towards the end of the talk, I will talk about analog quantum simulators and very briefly just mention some applications in the field of that I mentioned at the beginning, condensed matter, high energy, and chemistry. Okay, so I start talking about quantum algorithms. And so that's a typical problem that one considers with quantum and classical computers. So again, we are giving a lattice in any dimensions. We're giving a Hamiltonian that I'm assuming that it's local. We are giving some initial state. And so we always have to assume that this initial state is easy to prepare with a quantum computer. So for example, it could be a product state. All the spins are down. something like that. And what I would like to know is to compute how the dynamics occur. So if I evolve my state according to Schrödinger equation given by the Hamiltonian, generated by the Hamiltonian that I'm given, and I want to compute the expectation values on physical properties, so I want to compute some observable. So how can I do it with a quantum computer? Yeah, okay, so I'm giving a state, I'm giving the Hamiltonian, I want to compute some physical property after some time. And the first scientist who addressed this problem was Seth Lloyd in 1996. And he gave an algorithm, a quantum algorithm, that showed that this could be done efficiently. And by efficient, it means that apart from having only memory that grows like n, like the size of the number of qubits, not exponentially, also the time grows like polynomially in n instead of exponentially. So there's a huge gain in simulating dynamics. And the idea was very simple. So he just said, well, first, let me prepare my state with my quantum computer. And then if I want to evolve, let me trotterize the evolution. What it means is that divide the time in very small time slots. And in each of the time slots, then you can approximate the evolution in a small time by some quantum gates. And then at the end, you can translate into quantum gates the evolution. Then you will have, I don't know what I did now. So then you will have, your quantum computer would be in this state. So after that, just measure your observables. If it's magnetization, measure some spin, then repeat, measure again, repeat, measure again, repeat, measure again. And at the end, you will have this expectation value. And the time, the computational time that it requires to do that, then it will scale with the number of qubits that you have in your system, the time that you have everything squared and divided by the error that you will make in this observable. I think that there is an epsilon square here. But anyway, so you see that it scales linearly with n, and otherwise quadratically with n, and polynomially, let's say, with one of these over the error. Now, in the meantime, people have looked at some other algorithms, and there are now much more efficient algorithms. So the state of the art is an algorithm for which the computational time in a quantum computer scales linearly with n, and linearly with the time that you want to simulate, and logarithmically with 1 divided by the error. And you cannot do better than that. So that's a tight bound. However, I mean, this, and this should be compared, as I mentioned before, with this 2 to the power n. Right, it is a classical computer. So there is a very huge, very big speed up in simulation of these systems. These algorithms are, so the first one, the one by Seth Lloyd, this trotterization, actually is something that it's not very natural for these devices. And the reason is that by trotterizing, then there is a lot of overhead in gates. So you have to do many gates because you only have very, very short times. And every short time you have to do many gates. So, but still, I mean, there is hope that with these devices, you can use it in order to compute things. But what I'm saying is that, so this is not the natural environment for these devices because there is a huge overhead in gates. For the second one, it's even worse because you have to use, I mean, phase estimation, many other algorithms that require a much complicated dynamics. However, with analog quantums simulate quantum computers, then it's straightforward. You don't have to, I mean, you just don't even have to trotterize, just, I mean, engineer the interactions in your system in such a way that your qubits are described by the Hamiltonian that you want to solve, and then just let it evolve, don't do anything, and then measure at the end. So that's why, I mean, quantum dynamics is something that is very natural for analog quantum computers. And in fact, I mean, there have been experiments with people with cold atoms in optical lattices and with trap ions and so on that are very hard to replicate with classical computers, and that's on this simulation. Okay, so what about the ground state? Now we're interested in looking at zero temperature. And so for that, we have to introduce something that you know very well. So if I'm giving the Hamiltonian, then I will have the spectrum of the Hamiltonian. This would be the eigenvalues of this Hamiltonian. And there is the lowest one. And the corresponding eigenstate is called ground state. And so we are interested in the physical properties of the ground state, which correspond to the physical properties of my system at zero temperature. And the problem that one wants to solve is that, again, somebody gives me some observable, and I would like to predict what is the expectation value of this observable in the ground state of my Hamiltonian. And this would be, again, this observable could be, I mean, some correlation function, some magnetization, some whatever, I mean, conductivity, whatever. So this would be the physical property that I want to predict with my system. Well, it turns out that this problem is extremely hard even for quantum computers. It's a problem that was shown to be QMA hard. And I mean, without entering details, so probably you're familiar with the fact that in classical computation, the complexity of the problems is classified in terms of some classes. So there is the P class, these are decision problems that can be solved in polynomial primes, and P class, which are the class of problems that cannot be solved in polynomial time, but can be checked in polynomial time. And this QMA is the equivalent with quantum computers. So these are, roughly speaking, problems that with a quantum computer, very hard, they're exponentially difficult to solve. However, they're easy to check with a quantum computer. So it turns out that this ground state problem is related to this QMA hard. So it's, I mean, a quantum computer would take an exponential time in general to solve this problem. So the best algorithm that we can aim at would be something like scales like 2 to the power alpha n. And of course, depending on how much this alpha is, then we can have a relatively good algorithm or a bad algorithm. So if this alpha is 100, then it would be very bad. We will not be able to use it in 2 qubits. If this alpha is 10 to the minus 6, then probably we can have many, many qubits and still solve the problem in some time that is reasonable. So the question is, how much is this alpha? And so there are many papers in computing, I mean, proving how much, what is this alpha? And so it's here. So for example, some years ago, we built an algorithm which scales like 2 to the power n half, where this alpha is 1/2, right? And there is little hope that it would be better than that. So I guess that's what we have to live, that in general, these problems will be difficult. Apart from that, this algorithm, but this has to be compared again with a classical computer. And with a classical computer, if we assume that the computer can only use n bits or polynomially n bits, then the time there is super exponential. So that's what I said at the beginning, that if you restrict the memory of the classical computer, then you have to pay time. So even in that case, for these many body problems, you see that there is an advantage with a quantum computer. You put them on equal footing, even for the ground state. Now, these quantum algorithms for the ground state, I mean, they are very complex and they are not applicable to NISQ or analog devices. So they would require a fault-tolerant quantum computer. Okay. However, there is another set of algorithms for ground state, which are what are called heuristic algorithms. So these are algorithms for which you cannot prove that they will work, but they may work. And so they're very popular now, because it may happen that by chance you use this algorithm in some particular problem and then it works better than a classical computer. So one of them is the adiabatic quantum algorithm. And the idea is that you have the Hamiltonian for which you want to prepare the ground state. What you do is that you consider another Hamiltonian, which is trivial. This Hamiltonian, for example, doesn't have interactions. Then you prepare the ground state of this Hamiltonian. That's very simple. This would be all spins down, for example, here, or all particles in 0. And then you interpolate between these Hamiltonians, right? Just changing some parameter. And if you do it slow enough, then the ground state will be mapped into the ground state of the second system. And so this is what is called adiabatic evolution. And actually there is a theorem in quantum mechanics that as long as there is no crossing, then if you do that sufficiently slow, then you will be able to prepare the ground state of the target Hamiltonian. So the idea would be that you start with this product state, then you start changing your interactions, and you do the evolution with respect to that. Now you can use the algorithm for dynamics to do this evolution, this trotterization, or you could use an analog quantum simulator and change physically the Hamiltonian as a function of time. And if you do it slow enough, then you will prepare the ground state. So the problem is that the time for the adiabatic algorithm depends on the gap, depends on the energy difference between the ground state and the excited states. And for many problems, this gap decreases exponentially with n. So this means that the time in order to prepare the ground state will scale exponentially with time. However, for some other problems, maybe this is not the case, and that's where there is the hope that this will work. In fact, with experiments in atomic physics, so people have used this algorithm to prepare certain ground states in many body systems. There is another set of algorithms under the name variational algorithms.
Ignacio,
yeah.
Can I ask you a quick question?
Yeah.
So I should know myself, but it's good to know also your viewpoint on that. So how did people solve the issue of critical points? The quick thing is that even if you have a gap closing, you can simulate in the lab systems with so very few constituents that the gap is always finite. Or would you, let's say, I mean, which is the state of the art on the issue of?
Well, you see, for critical systems, the gap closes like 1 over n,
right,
typically, or 1 over n squared in the,
right,
for typical cases. So
right,
this means that the time would still be polynomial. So for critical systems, then you could go through a phase transition with a polynomial overhead. That's okay. The problem here is when you have something like spin glasses. In spin glasses, the gap decreases exponentially, and that's what it takes very long. And in particular, there are people who are trying to solve encoding classical optimization problems in quantum Hamiltonians. And these problems are very much like spin glasses, that this is way they always encounter these exponential gaps, and then that there is not so much advantage.
Interesting, very interesting.
Okay, so
may I also ask real quick, how do you deal with level crossings as on top of your plot?
Well, if there is a level crossing, then there is no hope. Okay, so you have to make sure that you don't have many symmetries, and that's why you try to break the symmetries and to put even a little bit of randomness to avoid crossings. Okay.
But this is fine, right? A lot generically, you don't have crossings.
Exactly. Well, if you don't have a symmetry,
it's non-integrable.
You will not have.
So this is.
Well, there are some crossings shown on this figure.
Shown, but
yes. Well, I mean, you see, maybe at the very small scale there are anti-crossings, and you don't see them at the scale. Anyway, so the other method is variational quantum algorithms, and then the idea is extremely simple there as well. So the idea is that you take in the state 0 of all your qubits, and then you applied a set of gates. And this set of gates will depend on some parameters. So, I mean, physically, they depend on the time of your lasers, something. And so, of course, if you apply these gates, then at the end, you will prepare some states. And so what you do is that you measure the energy of the state, and then you optimize these parameters in such a way that you minimize the energy. So it's like the variational algorithm that we use in quantum physics, but now with a quantum computer, that the parameters of the circuits are the variational parameters. That's also very popular at the moment. However, one has to say that there have been also many papers just talking about many caveats of these quantum algorithms, of these variational algorithms. One of them is that you have to measure, you have to do many measurements on them, with maybe 10 to the 14, 10 to the 15, or 10 to the 20, or something like that, which is out of the possibilities of any experimental setup. Okay, so now maybe here a paper that we posted recently on the archive. It tries to get the best of the variational and the adiabatic and combining in what we call variational adiabatic algorithm. So hopefully we get the best of both, not the worst of both. But the basic idea there is that what you do is that you take your adiabatic algorithm that you had before, and in which you change adiabatically some parameter, but now you cut the time or the parameter in different slices. And now what you do is that you use these slices or the time that it requires to go to one slice as a variational parameter. So what you do is you go on one slice slow, then slower, then slower, then the next one faster, and so on. And then you optimize with respect to the total time in each of the slices. And then these are the variational parameters, only those times. And so what happens is that you require very few measurements, and then you can accelerate the quantum, the adiabatic algorithm with that. In fact, what we propose is first to use this method to do adiabatic spectroscopy. And the idea would be very simple. So imagine that you start with the adiabatic algorithm, and then you change, go to this point, and then go back, wait a little bit, and then go back. Okay, and then you measure what is the probability that you ended up with the state you started with. So you can measure all the qubits, and if they are 0, then the probability is 1. And so what you can do is now to fix this probability that you go back to the right state and compute what is the time that it requires then to go back and forth for that, and plot this time. And if you plot, yes, I mean, for some particular model, we did it for some particular model with 50 qubits, if you plot the derivative of this time as a function of the parameter, then it turns out that you get, I mean, basically what you get is what is the cap, the properties of your cap. So there is a way of just first checking what is I mean, how is your spectrum, And once you have that, then you can do an optimization, better optimization with respect to these parameters. And that's one example with 53 qubits for this particular model. That's a non-integrable model in one dimension, and in which you do in order to get some fidelity at the end. That's so this would be like the error that you get at the end as a function of the total time of the algorithm. You use the normal adiabatic algorithm. It takes this time. And with this method, you see that you can gain a factor of 10 in time in order to get the same error, the same fidelity. And of course, for this kind of first generation of devices, I mean, decreasing by a factor of 10 the time can be a lot. And that's why we are collaborating with some experimentalists now in Misha Lukin's group in order to see how, with his system, to actually use this variational quantum adiabatic algorithm. Okay, anyway. So,
how do you do it experimentally? It's with Rydbergs?
Well, I mean, you start with a product state and you change adiabatically something.
Sure, no, the variational approach, sorry.
No, then you just have to measure. If you come back to you have to measure all the spins at the end. And if they are all spin down like they started, then you're doing well. And if not, then this is how you can, I mean, you can compute these times. So, I mean, the nice thing is that you don't have to measure energies. You don't measure energies, but you measure some other things that don't have big variance, and this avoids a number of measurements.
Okay. This is the advantage. Okay.
Yeah. Okay, so I was talking about dynamics, and dynamics. You see that dynamics is very important because first, there is a big advantage in dynamics, and second, the dynamics is typically used in other algorithms like this adiabatic algorithm, right? Because you have to do the dynamics. It's behind everything, this dynamics. So now I go to finite temperature. Okay, so now it's not zero temperature or finite temperature. So again, I mean, you given some observables and you would like to compute the expectation values at the finite temperature or finite energy. So what I mean now is that I have the same energy spectrum that I had before, but instead of computing properties of the ground state, but I'm interested in some properties somewhere in the spectrum, for example, here. And of course, if I fix the energy, then it's very likely that there will be no eigenstate at this energy. So I will give certain width. I will allow for a certain width in the uncertainty in my state, because I would like to have a state in the spectrum that has this energy. And this is one of the problems. This would be like what we call it's called micro-canonical ensemble. You fix the energy and would like to compute the physical properties of states at that energy. And the other one is just the canonical ensemble, in which you just give in the Gibbs state. And then you give a probability, Boltzmann probability to each of the states in your spectrum, depending on the energy, and then you would like to compute energy. So these are two problems that are very similar to each other. So one is compute properties in the microcanonical, and the other one is to compute properties in the canonical ensemble. And as you can guess, these problems are exponentially difficult for quantum computers because, in particular, they include the zero temperature. So if I would give you here t equals 0, then they would correspond to the state that I told you before that is exponentially difficult. And if I give you the energy, the one corresponding to the ground state, this would be exponentially difficult. So the question is whether you can do something in these cases. And you notice that if I would give you now infinite temperature here, then it would be trivial because it's a random state. And so the properties of random state is I mean, you can compute them classically. So you see that depending on the temperature, then the problem will be will go from difficult to something that is easy. And the same with this canonical ensemble. If I give you some energy in the middle of the spectrum, this would be very simple. However, if I go to the side, it's difficult. And the same thing happens with classical problems, because computing low energies is very difficult with a classical computer, not classical problems. And computing properties at infinite temperatures is very easy with a classical computer. So what happens typically is that there will be some transition at certain temperature, at center energy, then it becomes easy with a classical computer. And the same thing happens with a quantum computer. At some point, it will become easy. At some temperature, it will become easy with a quantum computer. So the question is where it is. So is the temperature at which this easiness in quantum appears much lower than the one corresponding to the classical or not? And so that's something that we have been investigating. And right, and so now maybe I formulate a little bit more. I don't want to be very formal, but I want to formulate a little bit more formally the problem. So the idea is that you're giving, again, the spectrum, you're giving some energy. And in fact, since we want to know so how the computational time scales if I make the system bigger, if I scale n, so if I grow n, then what we will have to fix is the intensive energy. So the energy per lattice site. You're giving the energy per lattice site, and you're giving some observable. And then you would like to compute the expectation value of this observable with a state which has as an expectation value energy, this energy density times n. So this is the condition of psi. And also that has a variance, this delta here, which is also fixed. Okay, so again, you're giving, let's say, some energy, you're giving some variance, and giving some observable, and you would like to compute this expectation value with some prescribed error, and you would like to know how the computational time grows if you grow the system n, and also how it scales with things like epsilon and delta and the variance. Of course, if the variance is very big, it's infinite, then it's very simple, no? Because it's a random state. And so then that's a little bit the idea. And so, I mean, just to say that if you connect to physical problems, so people have argued, so what are interesting values of delta? And in such a way that you would compute physical quantities that would correspond, let's say, to the microcanonical properties of the system. That's not so important here, but typically to have it in mind that this delta should be of the order of 1 over n. Okay, so if delta is of the order of 1 over n, that's when, I mean, you get interesting physical properties. This is when you will get properties related to the thermodynamics of this model that you're studying. Now, you can address this problem with a classical computer, and actually this is something that we did with David Hughes and some time ago. And we look at the complexity of solving these problems with tensor network methods, and it turns out that the complexity is very easy to show. That if you ask the variance to be very, very narrow, then you have a lot of entanglement. So the lower the variance, the bigger the entanglement. And so therefore, if you have very little variance, then it's very difficult to simulate this with tensor networks, which require little entanglement. And so the time scales like the exponential of 1 divided by the variance and the exponential of the number of particles. And as I told you before, the interesting regime is where the delta is 1 over n. So this means that for classical computers, to solve these problems then requires a time that goes exponentially with n, with the best algorithms that we know. And so the question is whether we can now solve with a quantum computer in polynomial time these problems. And the idea is, yes, so we had to propose some quantum algorithm. And this quantum algorithm, I just tell you what is the basic idea behind. The basic idea is that this is again the spectrum, so the density of states you want, and you're interested in certain energy. So the first thing that you have to do is to prepare a state with this energy. And this state could be a product state that has that energy. And you prepare a product state with that energy, it will have a variance. So it will not be an eigenstate, it will be a superposition of different energies, and this variance will be very big. In fact, this variance is very easy to compute. It's scales like square root of n. So this is not good enough because we wanted to have this energy. The mean energy is okay. That's not difficult typically. Well, I will talk about that in a second. But what is difficult is to make the variance smaller. That's what you require entanglement. And then the second part of the algorithm, what it does is that it makes it narrow. And so it applies a kind of a filter, like in optics. So you have a broad line, then you put a filter, and then at the end you make it narrow. So here the idea is that the quantum computer will do something very similar, applies a filter. And the third part is related to the fact that, in fact, you will not need to prepare the state that is resulting out of the filter, but you can just use what is called time series in order to do that for you. So you will have to compute some things that apparently have nothing to do with what you're doing here. You use your quantum computer to compute these quantities, and at the end you will combine them, and this will allow you to perform the calculation as if you had prepared the state. So the nice thing is that your quantum computer doesn't have to prepare it. And why do we want that? Well, because we want to use it with near-term devices, and with near-term devices, applying these filters and so on, it gets very difficult. So that's a way around it, that by doing some other operations, then we are able to do as if we had applied this filter. I know that it sounds a bit complicated, but it's not. But anyway, so let me just make a comment of each of the steps. So the first comment right away is that, of course, for that, it requires that there is a state that is easy to prepare with this energy, and this puts some restrictions. If I give you the ground state, then you should be able to prepare the ground state, and the ground state is hard to prepare, so this is not possible. But this is a restriction that must be there because, as I mentioned before, this problem is QMA hard. Okay, so that's a restriction to this range of energies, and so we can put bounds and so on. So what are the range of energies that we can address with that? The second is this filter. Well, I mean, what we did is we took a Gaussian filter. So we take the state, this is your initial state, for the product state, and then we want to apply this operator, which is just a Gaussian operator, which filters around the energy E with a width delta. And if you see, this operator is not unitary. And of course, that's the problem. Since this is not unitary, then you cannot apply it. However, it can be written as a series of unitaries, like a Fourier series. And so therefore, you see that here you will have the state, a linear combination of the state P evolve at different times. And now it comes the third point. The third point is that since at the end you want to compute some expectation value, then you don't have to create this linear combination, but you just have to compute the evolution with different times. You compute many matrix elements, and then at the end you do the classical computation. So in other words, what you will have to measure in your experiment will be this quantity and this quantity for different times. And if you're able to measure this quantity for different times, then you can put them in the formula, and this would correspond to having prepared this state and make the measurements. And now, because you can, well, and in practice, so to measure these quantities, this is a kind of Loch-Schmidt echo. I mean, there are several details, but the idea is that you will start with some initial state, then you evolve with your Hamiltonian, then you measure your qubits again, and then you see what is the probability that you are in the original state. And with that, you can compute things like that. And these are the ones that you put into these numbers, and these are the ones that allow you to compute these quantities. Anyway, so we showed in that paper that actually there's a poly algorithm. So the time in a quantum computer grows like polynomially with n, with now 1 over delta and 1 divided by epsilon. So you see that if delta, if the variance is 1 over n, this is a polynomial algorithm. So it's an exponential speed up with respect to the best known classical algorithm. Okay, for the canonical ensemble, actually, I don't have time to, and it's very complex, but the nice thing is that you can do something very similar. So basically, you can choose energies, run this microcanonical ensemble, and then sample with respect to energies, and also sample with respect to product states. So this means that it's like a Monte Carlo method, like the Monte Carlo method that people use in quantum physics or in classical physics, in which you take samples, then depending on the sample, when you sample one particle, then you choose another move and you accept it or not, and then you take another one. So here is very similar. The only difference is that in order to accept the moves or not to accept the moves, then you use the quantum computer. And actually, that's the problem with quantum Monte Carlo. You have heard quantum Monte Carlo for many problems has so-called sign problem. And in those problems, it doesn't converge, it doesn't work. And the reason is because when you're using this Monte Carlo method in a classical computer, when you want to accept or not accept moves, then it turns out that this problem gets exponentially difficult, so you cannot compute it. And so here the idea is to overcome this problem for the quantum Monte Carlo using the quantum computer as a subroutine. Okay, so this method is based on classical Monte Carlo. It uses the quantum computing as a subroutine based on what I told you before and the ideas that I told you before, and this circumvents the sign problem. Okay, so in summary, and I mean, nice thing is that, I mean, this can also be used with analog quantum computers and these devices. So in fact, we are now collaborating with some companies that have these devices and analog quantum and groups that have analog quantum computers and trying to implement these methods to compute things at finite temperature. Okay, so in summary so far, so what I've been saying is that there are problems like the dynamics. The dynamics are very friendly for quantum computers and analog quantum simulators. There is the ground state, which are very unfriendly, still much more friendly than classical computers. However, there are these heuristic algorithms. And there is a hope that with these heuristic algorithms, they will allow us to study physics or chemistry with these systems. And now if we go to finite temperature, then it turns out that also using the dynamics in the background, you can do dynamics and you can do a couple of things, then you will be able also to compute expectation values of properties at finite temperature. So I think that I don't have so much time, but let me just mention a couple of things about analog and digital quantum computers. So analog quantum computers, so I mean, many of the companies that are building quantum computers, they build digital quantum computers, but in many research groups, there are analog quantum computers. And actually, they have their advantages with respect to digital quantum computers. I mentioned one that is very important, that for dynamics, then you don't have to trotterize, which in digital quantum computers gives a huge overhead. So you have an analog quantum computer. I would say that for many body problems, it's very well suited. In fact, I mean, of course, the analog, they are not universal typically, so you don't have access to everything with your quantum computer, and so that's a drawback. There is no error correction, and so that's another drawback behind these computers. So then at the end, you have some errors, and you have to live with that. But they are easy to build. That's what I mentioned before, and they are very well behaved with respect to these dynamics. But I just want to make a claim or a remark that people sometimes ignore about analog quantum computers, which I think from my point of view makes them more interesting for many body problems. And the idea is that in many body problems, so typically we are interested in observables that are intensive. So you would like to compute what is the energy per particle, the spin per particle, the magnetization per particle, two-body correlation functions and things like that. This is where the physics is. And this makes a sense, because in a quantum computer, you are factorizing a number, then you have to measure all the qubits. So just like a many-body quantity that you're looking at. And this makes a big difference. So, for example, if you have an analog quantum computer that wants to simulate this Hamiltonian, and now there is an error, and there is an error in each qubit, then the total error that you will have will be n times epsilon, because there are n qubits. And so even if the error is very small, if n is large, these errors will be very big. And so you will have errors. So many qubits will not be right. However, if you compute at the end some observables, if 10% of the qubits are in the wrong state, then this observable, the error will be 10%. So you will see still the physics up to with an error with 10%, which is already enough to do things that you cannot do classically. So you tell somebody, compute the conductivity of the Hubbard model at 0 temperature. With 10% error, with a classical computer, then it cannot be done. So that's why these systems are very useful. And so I had an example of something like that. I don't have to talk about, but just in the last couple of minutes, just let me tell you something about physics. So now, what problems could we solve with these systems? I talk about condensed matter, high energy, and quantum chemistry. What about quantum simulators? Well, you have different sites. There are trap ions, analog quantum simulators, there are cold atoms, and so on. Let me concentrate in the case of cold atoms. In cold atoms, problems in condensed matter physics that are local are very natural, because the Hamiltonian right away, you put atoms in optical lattices, then they obey the Hamiltonian. So the simulation is relatively simple. It's also very flexible, because you can use boson, fermion, spins, geometry, and dimensions. That's something that is well known. And there have been some simulations with cold atoms of condensed matter physics problems. What about high energy physics? Well, this is just like the next step. It gets more difficult, and the reason is that the models in high energy physics are like the ones in condensed matter physics. They are local. However, they have Plaquette interactions. So you go to more than one dimension, then there are four-body interactions. And so atoms don't like four-body interactions. They have typically two-body interactions. So if you want to simulate four-body interactions, then you will have to do perturbatively. And so that's why this gets very difficult. Still, I mean, there are hopes that with analog quantum simulators, maybe you can simulate, and there are people working on that, lattice gauge theories in more than one dimension, which would go in the direction of high energy physics. And the last comment I wanted to mention is that we wrote a couple of years ago a paper on analog quantum simulation of quantum chemistry, in which you show that at least in principle, it would be possible to simulate simple chemical problems with molecules with cold atoms in optical lattices. And the idea is to use, instead of the electrons that would be in the molecule, to use fermion atoms. Then that they move in on a lattice so that they can have some kinetic energy in the same way that electrons have kinetic energies. Then, I mean, under the Born-Oppenheimer approximation, you assume that the nuclei are fixed. So this could be emulated by a laser that attracts these fermionic atoms to some point. And in this case, then this will act like the nuclear, the fermions like the electrons. And the main problem, the one that is non-trivial, is how to induce electron-electron interaction, how to make two fermionic atoms to interact with a Coulomb law that decays 1/r. We know that atoms don't like 1/r, and they are neutral, so they don't like 1/r. So the people in Mainz working on ions, you have 1/r in the ions. even though for quantum computers it's more like dipole-dipole, so it goes like 1 over r cubed. So how you can get 1 over r interactions in one system? And so what we propose here is to imitate nature. You have two electrons, the 1 over Coulomb interaction, it's coming from exchange of photons. So you write quantum electrodynamics, then you will couple the electrons to the photonic field, the other electron to the photonic field, and because of exchange of photons, then this induces an electron-electron interaction that scales like 1 over r. And so it turns out that with atoms, the same thing happens. So you have now two fermionic atoms and one boson atom that interacts with both of them. It can induce, under circumstances that we studied here, the interactions that decay like 1 over r. And therefore, in this way, you could simulate or do some simple simulation problems of quantum chemistry. So with that, I'm finishing. So I was talking about quantum simulation. And I was mentioning some algorithms for quantum simulation. But one can ask you a question, so why should we do quantum simulation? What is the goal of quantum simulation? Is it because we want to solve problems that we cannot solve with classical computers? I'm not sure about that. I'm not sure that this is the most important problem. So for example, many years ago, people were saying, you see, we want a quantum simulator because we want to solve the Hubbard model. But what happens if tomorrow somebody comes with a tensor network algorithms, and actually some people have come up already, that solves the Hubbard model? Does it mean that quantum simulation is not useful? No, I think that on the other hand, it can be very useful because it, on the one hand, can provide understanding. So you have a physical system that is emulating the physics, and you can change and understand phenomena there of that system that you would not understand just with the solution of a computer that is coming out. But what is even more important for me, there's a way of benchmarking theory. So there are many theories for quantum chemistry. There are many theories for many body systems, but most of them, or all of them, cannot be benchmarked because we don't have an exact solution for big systems. And if you had a quantum simulator, this would allow us to, together with experiment and theory, to evolve and develop much better theories for many body systems that are things that are lacking. So quantum simulation has many challenges, and okay, so here I mean, of course, experimentalists know that they are very difficult. So what I was mentioning here with the algorithms in practice is very difficult. However, if you compare these challenges to the challenges of building a scalable quantum computer, I think that there's still a big difference. And with that, and a picture of my department in our last retreat. So I'll stop. Thank you for your attention.
Thanks a lot for the very nice talk. I'm just wondering where that retreat was. Looks like.
So this is Gather. This is this computer program that can emulate the fact that you can meet in coffees and things like that. So we had even games there and talks online. So this was everything done online.
What is it called, the program?
Gathering, or Gather, something like that. It's very popular. It's actually it's very good because you can have podiums. You go to the podium, then there are some rooms where you can talk, the poster sessions, and so there are many possibilities actually.
All right. Yeah, thanks for the talk, and I'm sure there are questions. If you have a question, you can raise your hand. And oh, Ferdinand has a question. Ferdinand raises his hand. Yes. So yes, Ferdinand, go ahead.
Yeah, thank you, Ignacio. Great talk and great presentation of quantum simulation. If I come to this chemical simulation, so you show that you can do in principle chemical simulation, but if somebody from chemistry industry would ask you to simulate now ammonia or whatever, or water even, then how would this be implemented in this situation? Is it really possible to put as many laser beams as nuclei, or have you thought about how to implement these different orbitals? I just think the quantum simulation is wonderful if the situation is fitting to the nature of the problem. But once it becomes more specialized, so to say, no longer a fundamental problem, but rather something which is really here is a hydrogen, there's an oxygen, then I think the versatility of a quantum computer is still ahead, and then of course you have to pay the cost for this. So what is your idea about this?
Okay, so the idea is depending on whether you want to compare the difficulty with a fault-tolerant quantum computer or with a NIST device. So if you want to compare with a NIST device, probably a NIST device with 100 qubits is easier than this experiment. So these experiments, the rule of the thumb that if you want to have something like, 5-atom molecule, 6-atom molecule, which would be already competitive with the best methods that you have, then you will have something like 100 by 100 by 100 lattice sites, which is, as you know, that is very difficult, or it's impossible at the moment, right? But that's so much more difficult than the NIST device. However, as compared to a scalable quantum computing, what you have to have, 100 million and 10 to the 16 gates, then probably is much easier. And so the scaling here is polynomial. That's the good news for the simulation. However, like the polynomial physical in practice doesn't mean anything, right? So what we estimated here, so what we claim here is that first of all, when you should do like in any experiment, you should start with a simple case as a hydrogen atom. And with the hydrogen atom, then you could see the physics of the hydrogen atoms, even in 2 dimensions. You don't have to go to 3 dimensions, just in 2-dimensional lattice. You will see the Lyman alpha. All the physics is there and should be able to see it. And this would require an existing lattice. This would not be difficult at the moment. The next thing would be like the hydrogen molecule, in which you will have 2. And then you should see effects related to the dissociation. And for that, you also need something like 20 lattice sites, 20 by 20 in 2 dimensions. And from then you can start just putting 3, and then 3 you have conical intersection. So you see, you can increase the difficulty. And at the end, if you experimentalists, you're very clever, then you will find tricks of doing that. Then you will be able to scale it to 100 times 100 times 100. The problem here is discretization. So it's really not only that you have to put all these lasers, which what we did is here to consider and did the calculations explicitly using holographic methods. Like the ones that Antoine Brouwer uses for his optical lattices. You can use them here also to create potentials, right? And we computed the errors and things like that. And so that's not the most difficult part. The most difficult part would be to have 100 by 100 by 100 in which there is a lattice without a potential and so on. And that's I would say. So I would say that you asked me ammonia. This will not be done in the next 10 years probably. But however, the experiments related to the physics of atoms and molecules, simple molecules, will be there. And if it's successful, then one can go and try to go beyond what you can do. But apart from that, maybe that insist on that. What for me this would be useful is if it can be used as a benchmark for my classical methods for DFT. Just take 4 electrons, 4 atoms, and 2 nuclei. And use DFT, and you will see that it will not work well because, for example, dissociation is not well expressed in terms of DFT. But you can learn how you can do it because you have now a system that you can benchmark your theoretical methods. That's what I was insisting in my last transparency.
Yes. And actually, another question which is related to this: if you do this with qubits, then you have to go through the pain of the Wigner-Jordan transformation because you are at the end simulating electrons. They have the fermionic behavior. So do you have a trick to do gates with ions that are fermionic by nature?
Well, there is a trick. So with Frank Verstraete, we wrote a paper in 2006 where we showed that if you put an overhead, then you can simulate fermions with bosons locally, with local interactions. So as you say, you do Jordan-Freeman transformations in 1 dimension, that's okay. Then, everything remains local. But if you do it in 2 dimensions, then you will have to induce gates that are non-local. However, what you can do is to put some additional particles, some ancilla. Per each qubit, you put an ancilla qubit. And with this overhead, then you can transform the problem into a problem that is bosonic.
Okay, I have to look at this paper. Maybe you send me this reference.
Yeah, I can send the reference, and I tell you that some people have considered other methods. This was very long ago, and so that's one of the ways around, let's say, quantum simulation. The problem is that you require 4-body interactions. Of course, for ion traps, this 4-body interaction is not as crazy as for atoms, right? Because there are ways of doing that.
Sörensen in a 4-ion crystal does the 4-body interaction basically.
Okay, yeah. So that may not be crazy. Yeah.
There's another question by Ramir.
Yes, thank you, Arne. Hi, Ignacio. So I will ask you a generalistic question, and I will ask actually 2 questions. You choose which one you want to answer. And if there are no other questions, maybe you pick up also the second one. So your opinion on this business of hybrid circuits, what can teach us about quantum computing? I'm sure you know what I'm talking about, this Use-Fisher intercalating projective measurement for unitaries. How much is realistic? What can inform us about that was not known before? And the alternative question is your perspective on dissipative state preparation. Why this didn't really fly? Because there is a lot of theory. By dissipative state preparation, I mean the fact that you can try to build the correlated states with Lindbladians, and so you convert part of the dissipation into a resource rather than an enemy. And what would be missing, in your opinion, to make this fly? And whether instead it will remain forever a theory idea? Thanks.
Okay, that's both very interesting questions. So I'll answer one, and if there are no more questions, then I will answer the other one. So
choose which one upon your preference.
And let me go to the dissipation. So the dissipation, actually, preparation of states has a big advantage with respect to the other type of preparations. And the idea is that you can create states that live forever if you have dissipation. So you could create an entangled state that is entangled all your lifetime. And this has been done. I mean, there is an experiment of Eugene Polsik of entangling two atomic ensembles.
Yes, you are in the paper, right? If I know you, you're in the paper.
Yes, and he can have it for hours. So he can have entangled states of two atomic ensembles that if you, at any time, you want to see, they are entangled all the time. And that's only possible if you would do it in that particular way. So the idea is that there is a, I mean, even if there are errors, there is an attraction point. You have dissipation, then it's like, I mean, like in classical nonlinear dynamics, there is a point you want to go to it. So if there is a little bit of noise, then you come back and say you're around this point. Of course, there is some attraction region. And so what happens in some experiments is that the noise is bigger than the attraction region, and this is why it gets difficult. But if you manage to have some attraction region, for which the errors is not important, like Eugene did in his experiment, this is a good way of preparing these states. Now, the second question is, why do you want to have these states? Okay, so that's and the states could be used for metrology or something else, but that's a different question.
And this is not my question. Thank you.
Yeah. Okay.
Thank you. Are there other questions?
By the way, while people think, I want to say to Ferdinand that I invited Arguello, which is the first author of this Nature paper, to talk at our next theory colloquium. So I will give us 1 hour presentation on quantum chemistry. And you can ask him more detailed questions. I chatted with Ignacio about it some months ago.
All right. Are there no other questions? Maybe I can do two things. I can ask some more general questions. For once, I can also announce next week's seminar while you all think about questions. But what I wondered is, just looking at your resume, and I probably just have just looked at the top front page of Google Scholar, and I of course know you from a lot of tangential contributions. I mentioned that you have contributions to simulation, to computing, to communication. What about sensing?
Okay, so there's a paper. It's not so excited, but I think that I have a paper together with Artur Eckert, Martin Plenio, Susana Huelga, and so on. That was in 1997, which was, I think that was the first paper that noticed that if you are doing metrology and you have noise, then the standard scenario, you lose everything. You see, because if you have a Ramsey kind of experiment, then you want to increase the Ramsey time as much as possible, because then you gain precision. However, you have dissipation, this restricts the Ramsey time. And if you have entanglement, this restricts also the Ramsey time in such a way that it compensates whatever you gain with the spin squeeze state or whatever. And so that was a paper that we wrote. That actually I think that it's highly that has some impact in the field. I mean, of course, there are many more papers that have more impact. It's not maybe, but I think that was an interesting one. So I work a little bit on sensing or metrology at least.
Okay, and then maybe as I mean, I should probably know that. So please forgive my ignorance. Also to Ferdinand, but mostly to you now. What is the current state of the art of quantum computing? I don't know. Is it because the last time I checked, people were talking about a 50-qubit quantum computer, and then I get actually questions from my friends asking, who are not physicists. I have friends who are not physicists, asking questions like, there's D-Wave now, Google, Facebook, and whoever is working on quantum computers, and does science in Europe actually have a competitive edge in these terms, or will this all be taken over in the future by a Google quantum computer? So what's the state of the art currently?
Okay, so first, you see, I mean, the quantum computing is not only about the number of qubits. I'm sure that Ferdinand can trap many ions, but if they are not under control, then it doesn't mean anything. So it's not the number of qubits in the control that you have them. And so then, I mean, we have the Google numbers are very good. They have of the order of 50 qubits, and the error per gate, that's a way of measuring, it's of the order of 0.3%. That's really great. I know that people with ion traps, they are able to get better gates than that. However, it's difficult to perform these gates in the presence of 50 ions at the same time, but that's advancing. So I think that this would be like the state of the art is of this order of magnitude: 50, 100 qubits, 1% errors, and there are different technologies, and but it will be very difficult to go beyond that. That's why one immediate question is, if you have this 100 qubits with error per gate of 1%, or maybe 500 with error per gate of this order, what can you do with them that you cannot do with classical computers? That's the big question. There are many claims that you can just invest in the stock market, and you'll do your investment portfolio with a quantum. But I don't believe most of these results. There are many optimization results which I don't believe. So there are very few that are solid. I think that one, it's very solid, is quantum simulation. So indeed, with this system, you could simulate things that you cannot do with classical computers. And beyond that, I don't know any other, even though it may happen that, in next month, IBM finds one particular application. So again, maybe to summarize, we have these NIS devices, they have 100 qubits, but the question is what to do with them. Okay, what can we do with them?
So thanks. So there is already some market where people, I think, provide this their quantum computers for other people to come up with algorithms to do certain things, right? So is this anywhere near commercially successful, or how long will that take? Maybe it's also too much to ask. It's like to speculate on this. But
no, there are companies appearing every day in the newspapers that will sell you a quantum device. Okay, well, you can buy you have 15 millions, and you can buy D-Wave. You have 10 millions for you can buy IBM, and they will. The IBM will have of this order of magnitude, 20 to 50 qubits with these error per gates of 1%. But of course, why should you buy that if there is not an application that you know? Well, you can buy them in order to try. And so this is what is happening. So many universities, or in case in Germany, the Fraunhofer Society has bought one of these IBM quantum computer to try. And the hope there is that if you leave scientists to try, they probably will not find anything useful. You leave industry try, or even entrepreneurs or young people who have other interests, they might find something. And so that's the big hope, and I think that everybody has this hope that there will be something that people will find that if you go to the academic environment will not be found. Saying that, one example is of something that was a surprise is this certified random number generations. Okay, so people have found that these quantum computers like Google could be used, or may be used, for certified random number generations, which in itself could have a market.
Great, thanks. So currently I don't see any other questions. That would be your last chance. I'm advertising next week's quantum seminar will be given by Ralf Rölsberger from the Hamiltonians Jena, when X-rays go to quantum, from cavity QED to quantum imaging. So something completely different, also nonetheless interesting. Any last question? That's not the case. Ignacio, thanks a lot for a very interesting talk. And hopefully we see you next time in Mainz, in person, maybe.
Yep. Thank you very much. Thanks
a lot. Seminars.
Thank you. See you, Ferdinand.
Thank you.
Thank you.